Let's imagine a lot of mice in a tunnel system. These mice can enter the system through S and leave the system through T. The arrows are the only direction the mice can go, and the capacity is how many mice can go through that part of the tunnel or edge during 1 unit of time. You have as many mice as you want to go into the tunnels, and you want to get as many mice out through the end of the tunnels as possible. This is an example of the max flow problem. One thing you could try is going from S to A to T. This will give you an output of 3 mice. Or you could try going from S to A to B to T. This would give you an output of 3. Or you could try going from S to A to T while going from S to B to T. This would give you a total output of 5. You can also split some, like if you go from S to A and then go from A to B to T, while going from A to T, giving you a total output of 5. However, the best option is to do this while sending 2 from S to B to T. This will give you a total of 7. For some of our algorithms, we might first choose a suboptimal path and then change our mind. Say we try sending out 5 mice to A, then we take 3 of them to B and then to T. This is actually how many mice go through each tunnel per time unit. There will be mice in all tunnels being used at the same time. So, let's try showing the number of mice going through the tunnel each unit of time and the output. Because we don't want mice getting stuck in vertices, we will only send as many as will get through. In this algorithm, the flow going into every vertex must be equal to the flow going out. Let's show the amount we have currently going through each tunnel. Using the Ford-Fulkerson algorithm, these mice can change their mind and not go through a tunnel. We often show this as a backward edge with a capacity of the number of mice in that tunnel that can change their mind. If a mouse goes back, the first number on the initial edge goes down, and the second number on the backward edge we created goes down 1. This is looking pretty chaotic. This is the way the information would usually be depicted. It's simpler, but I will miss the cute mice. The first number on the original blue edges will always be the same as the bottom number on the purple back edges. This is because the amount of flow going through the edge currently is the amount that can just not go if we want. Next, we look for another path using depth first search for Ford-Fulkerson from S to T. Let's send 1 from S to B to T. The only reason we only sent 1 through is because B to T only had 1 capacity available. This edge is called the bottleneck in this step. We can send another 2 from S to A to T. If we couldn't change our mind, we would be done. However, one of the most important factors of being smart is having the ability to change our minds, and we are smart. We can see another path from S to T in one of our back edges. We can send 1 more through here. When going from S to T, we know how to change the graph. When we are using this back edge, we add 1 on the back edge. But if 2 mice were to be crossing, they could instead decide not to go. Then we fix the numbers by, instead of sending 1 on a back edge, sending 1 fewer on the main edge. In code, these 2 steps are usually done simultaneously without taking memory for the back edges. Now that we can't find any more paths from S to T, and all of the back edges have 0 going through them, we can ignore the back edges because they weren't really there to begin with. This shows us the amount of flow going through each edge, giving you 7 flow as the max. Say we make a cut through the graph with S on one side and T on the other. There are two arrows going from the side with S, which is usually depicted as being on the left, to the side with the T. During 1 unit of time, there can be at most 5 going from C to E, and there can at most be 8 going from B to D. Because of this, there can at most be 13 going from the left to the right. This works even if we make really wacky cuts. Here we can see that this cut means there must be less than or equal to 20 flow. We don't include the edges going from the right back to the left. This is because we are trying to pass as much on as possible. Even if the optimal solution were to include one of these edges, we will still only be able to push less than or equal to 20 from the left to the right. Of course, we already know that the max flow must be less than or equal to 13, which tells us more information than less than or equal to 20. The most information we can get is when the number is the lowest. The cut with the smallest total is called the min cut. This tells you the max flow. Even though a lot could get to E and F, they can only pass on 3 during one time unit. Please like and subscribe.